Welcome back to our APES Flipped Classroom. We're continuing with our lessons in Unit 4. And today we're going to be talking about the atmosphere and about our global wind patterns. So let's begin with the atmosphere. We're going to learn about the major gases that make up the atmosphere, as well as the layers of the atmosphere. So first, let's talk about the major gases in the Earth's atmosphere. Obviously, the largest content by far in the Earth's atmosphere is nitrogen, and that's about 78% of the Earth's atmosphere. And that's in the elemental form, so that's the N2 molecule. And we remember from learning about the nitrogen cycle that this is unusable to plants unless it is fixed. So unless it goes through all of those processes of nitrification and is then available to plants. Okay, we also have oxygen. That's the other major component of the atmosphere. It's produced by photosynthesis in plants and phytoplankton. It's needed for human and animal respiration. So the amount of oxygen is incredibly important. We tend to think of photosynthesis in plants as the primary contributor to oxygen in the atmosphere, but the reality is that photosynthesis by phytoplankton is actually the #1 contributor to the amount of oxygen in our atmosphere. And it is the phytoplankton in the ocean that generally keep our oxygen levels very constant. 0 to 4% of our atmosphere is made up of water vapor. Obviously, this is going to vary by the region in the Earth, by the conditions. Is it hot? Is it cold? It does act as a temporary greenhouse gas, but it's less concerning than carbon dioxide. And the reason that it's less concerning than carbon dioxide as a greenhouse gas is that it is regulated by the water cycle. And so once the air starts to cool down, then we reach the saturation point and water vapor will condense and it'll rain and it'll come back to a standard condition. So even though water vapor is a greenhouse gas, it's not one that is increasing because it is controlled by the water cycle. Now, as global climate change is happening and our global temperature is increasing, then the amount of water vapor is going to increase slightly, which of course is then going to be a positive feedback loop with greenhouse gases. Water vapor cycles very quickly through the atmosphere. It evaporates, condenses, rains, begins the cycle again. A very small percent, less than 1% of our atmosphere is argon. It is a noble gas. It's inert. We can't see it, smell it, taste it. It doesn't interact with anything else. It's just there. And then the final one that we're going to talk about is carbon dioxide. It is less than 0.04% of our atmosphere. However, it is the most important global greenhouse gas. It leads to global warming. It is removed from the atmosphere by photosynthesis, but it's put back into the atmosphere by cellular respiration, by the combustion of fossil fuels. Okay, so those are the gases in the atmosphere. It is important that you know those relative percentages. They like to ask questions about those as far as multiple choice. All right, let's talk about the layers of the atmosphere. So I'm going to teach you guys a little mnemonic to help you remember this. I always start closest to the Earth. It goes troposphere, stratosphere, mesosphere, thermosphere, exosphere. And to remember that, we can say thou shalt memorize this early. T for troposphere, S for stratosphere, M for mesosphere, T for thermosphere, and E for exosphere. So let's start with the characteristic of the layer closest to the Earth. Excuse me, that would be the troposphere. Tropo is Greek for change, and we call it that because the troposphere is where we have the weather. It is the most changeable layer of the atmosphere. And it's from 0 to 16 kilometers from the Earth. It is the most dense layer of the atmosphere because there are so many layers on top of it, and the pressure of all of those molecules pressing down makes the troposphere the most dense layer. Because it is the most dense layer, almost all of the molecules of gas in the atmosphere are actually found in the troposphere. In the troposphere, weather happens. This is the air that we breathe. This is the air we interact with. Ozone in the troposphere is harmful to us. It is a respiratory irritant. It can cause asthma. It damages plant stomata, which is the little pores that they essentially breathe through, and it forms smog. So ozone in the troposphere is bad. Now, moving up from the troposphere, we enter the stratosphere. You can remember S for second. It's between 16 and 60 kilometers from the surface of the Earth. It is less dense than the troposphere because there are fewer layers, fewer molecules above it. The ozone layer, the thickest area of ozone, is found here. Here in the stratosphere, the ozone is good because this ozone we're not breathing in. It's not affecting plants because there aren't any plants above 16 kilometers. And it absorbs both UVB and UVC rays. So that's ultraviolet B and ultraviolet C. And those are the portion of the electromagnetic spectrum that cause cancer. They mutate DNA. And so we rely on the ozone layer to protect us from UVB and UVC radiation from space. So in the troposphere, ozone's bad. In the stratosphere, ozone's good. Above the stratosphere, we have the mesosphere. That's our middle layer. It is even less dense than the stratosphere. This is where we have shooting stars. That's pretty much all we need to know about the mesosphere. The thermosphere is the hottest layer of the atmosphere because it is absorbing X-rays and UV radiation from space. So it's incredibly hot because it's absorbing all of that radiation, even though it has very, very few molecules. The mesosphere is very cold because it has very few molecules, but the thermosphere, because it's absorbing those X-rays and UV radiation, is very hot, hence its name thermo. This is also where we get the charged gas molecules that glow because of that solar radiation, and that's what produces what we call the northern lights or the aurora borealis. And the exosphere is the outermost layer. This is where the atmosphere merges with space. Okay, let's talk about temperature in these layers. Again, we're going to start closest to the Earth. So the troposphere, as we get farther from the warmth of the Earth's surface, temperature decreases. So the troposphere is warmest closest to the Earth and cools as it goes up. As it becomes less dense, it cools. Then as we go through the stratosphere, we go past the ozone layer and we start having UV rays coming in, and the temperature begins to increase again. So as we go up through the troposphere, temperature decreases. As we go up through the stratosphere, temperature increases. Then as we go up through the mesosphere, because there are very few molecules here, the density decreases. There's few molecules to absorb heat from the sun, and it gets colder as we go up. The mesosphere is actually the coldest place on Earth. Then we move up through the thermosphere. Now, even though we have very few molecules here, we are absorbing that solar radiation. And so the thermosphere is very hot and gets hotter as you go out. The thermosphere is the hottest place on Earth. So as we go up, it kind of zigs and zags back and forth. Troposphere cools as we go up, stratosphere warms as we go up, mesosphere cools as we go up, and thermosphere warms as we go up. Okay, so here's your practice for 4.4. I want you to identify a layer of the Earth's atmosphere from the diagram that has an inverse relationship between temperature and altitude, and I want you to describe why this occurs. Okay, moving on to global wind patterns. So we're going to talk about what causes global wind patterns, and that's really three main characteristics. One is energy from sunlight. The second is the density properties of air itself and what happens when we have more and less dense air. And then the third one is the rotation of the Earth, which causes something we call the Coriolis effect. So properties of the air itself. Warm air rises. Warm air is going to hold more moisture than cold air. As air rises and there's less pressure on it from the layers above, it's going to expand. As it expands, there's fewer molecules bumping into each other, so it's going to cool. And the cool air can't hold as much water vapor, which is going to cause condensation, which will result in rain. And after the air cools and expands, it's now colder, which makes it denser, which means it's going to sink. So when we look at this, we have lots of direct sunlight right at the equator. That's going to warm the air and it's going to cause evaporation of water. And then as that warm air rises, it cools and expands. That water vapor is going to condense into rain, which is going to fall right back down onto the tropics. As the air continues to rise, it cools and expands. And now that it's cooler, and it's going to start spreading out both north and south of the equator. And that cool, dry air is now going to sink back down. And because of the other factors, Coriolis effect and pressure effects, it generally sinks down around 30 degrees north of the equator and 30 degrees south of the equator. So we have cool, dry air falling. And so that's why we see our desert biomes at 30 degrees north of the equator and 30 degrees south of the equator. That air coming down creates an increase in air pressure. The air rising at the equator causes a decrease in air pressure. So that means that the high pressure area is going to push the air back towards the equator, and we get this circulation that we call a Hadley cell, where the air rises at the equator and falls at 30 degrees north and south. There's that high pressure at 30 degrees and low pressure at the equator. Okay, now the Coriolis effect. So the Earth rotates, I'll know this, and it rotates from west to east. Because the Earth is rotating, that impacts things that are traveling through the atmosphere, and it causes a deflection. So our air is falling at 30 degrees. The wind between 0 and 30 degrees is moving from east to west because the Earth is spinning from west to east. And so that means that as the air is falling at 30 degrees and returning towards the equator, our winds are going to be from the east to the west. And so we're going to have that twist to our Hadley cell. Between 30 degrees north of the equator and 60 degrees north of the equator, winds actually move from west to east. And so we have a deflection again, because the Earth spins faster at 30 degrees north than it does at 60 degrees north. We have the same amount of distance to, same rotation, farther distance to travel. So it's moving faster. So these are our global wind patterns. Air moves out from 30 degrees to the equator and from 30 degrees to 60 degrees because there's this area of high pressure at 30 degrees and low pressure at 0 and 60. So the air that rises at the equator creates an area of low pressure, sinking down at 30 degrees, gives us an area of high pressure. Our winds blow from east to west. We have those eastern trade winds, and that drives the ocean current clockwise in the northern hemisphere and counterclockwise in the southern hemisphere. And these westerlies, these winds blowing from west to east, drive the weather patterns of North America. All right, here's your final practice FRQ for this one. I'd like you to explain how the sun is responsible for this pattern of air circulation. If you have any questions, as always, let me know. Look forward to seeing you.